In today's lecture, which will be the last lecture of this course, I am going to talk about a slightly different topic, and this has to do with errors and estimation of parameters. Okay. Now, in order to motivate this, let me remind you of an object that you have seen before, that is called a distribution function. So, suppose you have a variable x, and let us say this variable has a distribution function f of x. Okay. If the distribution function of this variable is f of x, then you know that this f of x will be a function. For example, suppose f of x is equal to e to the minus x x0 square by 2 sigma square into sigma root 2 pi. Okay. So, suppose this is a Gaussian distribution, and suppose so then what we you know that f of x has this form where x versus f of x looks like this, and if this is x0, then it looks like a Gaussian function centered at x0. Okay. So, it looks like a Gaussian centered at x0. At x0. Okay. And the standard deviation is sigma. Okay. So, then what do we mean by this distribution function? What we mean is the following. So, probability that x is between x and x plus dx is equal to f of x dx. Okay. So, the probability of finding x in an interval is f of x times dx. So, then f of x is the probability density or the probability distribution function. Okay. So, now what do we mean by this distribution function? What the way to think about this is the following, that suppose you have this variable x and you had a way to measure it. Okay. So, you measure it once, you will get some value of x, you measure it again, you will get another value, you keep repeating this measurement many times. Okay. So, if you repeat the measurement many times, then most of the times you will get values of x in this range. In the range where the distribution function is high, you are more likely to get values of x in this range, and you are less likely to get values where the value of the distribution function is very low. Okay. So, if you break this space into intervals like this, then most of the times you will be in this interval. Okay. So, most of the times you will be in this interval, most of the times you measure x, you will get somewhere around here, then lesser number of times you will get in this, lesser number of times you will get in this, and even fewer number of times in these. Okay. Now, this is what will happen if you make a very large number of measurements. Okay. So, if you make and how large should the number of measurements be? The number of measurements should actually be infinity. If you make infinitely many measurements, then the number of times you get x in any interval will be proportional to f of x times the size of that interval. Okay. Or actually integral f of x dx over that interval. Okay. Now, typically okay, so in any measurement, in any experiment, we measure some quantity many times. Okay. So now I want you to imagine that you are measuring this quantity x. Okay. So you do an experiment and you measure this quantity x. Okay. And you measure it once. First time you measure it, you get a value x1. Second time you measure it, you get a value x2. Third time you measure it, you get a value x3, and so on. And you do it n times, you get these n values. Okay. So n measurements of x. So this is what you do in any experiment. You might be, if you're doing a titration experiment in the lab, you try to repeat it many times. Okay. So same way any experiment that you do, you try to repeat many times till you get a significant number of measurements. Okay. Now the question is, what do we do with this? Typically what we do is we take an average and then we take standard deviations and so on. Okay. So now the question is, why do we do those things, and what is the correct procedure for doing them? Okay. So what we are trying to do is the following. We are trying to you have x has a distribution function, but you don't know what the mean is. Okay. You don't know what the standard deviation is. Okay. So x has a distribution function. Okay. X. Okay, is f of x. Now x has two parameters. It has x0 and it has sigma. Okay. So this is distribution function of x. Of x, and these are unknown parameters, or these are parameters of the distribution function. Okay. So now your problem is basically you want to estimate these parameters. Okay, you want to estimate these parameters from these n measurements. Okay, so the problem estimate x0 and sigma from n measurements. Okay. So this, in some sense, the goal of your experiment is to get the values of x0 and sigma. Okay. So you want to get the values of x0 and sigma. Okay. Now we have sort of turned around the problem. Instead of saying that we want to know the value of x, what we say is you want to know the mean value of x. Okay. And you want to know what is the standard deviation of x. Okay. So if we say that x is distributed, if you say that the distribution function of x has this form where it has where it is peaked at x0 and has a standard deviation sigma, okay, then you want to estimate x0 and sigma based on these measurements. Okay. So this in some sense is the crux of what we are doing in all our measurements. What we are doing in any measurement is to estimate the parameters. The parameters that we are estimating are related to the distribution function. Okay. Now you might say that you want to know what is the mean of the distribution function. You are only interested in, sometimes you are only interested in the mean of the distribution function. You want to know what is the most likely value of that function, okay, which is also the same as the mean, okay, in this case. Okay. So how do we go about estimating x0 and sigma from these measurements? Now the formal procedure is there is an area of work called estimation of parameters. it is using maximum likelihood methods. Okay. Now, we will not do the formal procedure. Okay. So, this is not something that we will be doing. We will simply use the results. Quote results and use. Okay. So now let's see what are the results that we are interested in. Okay. So the first thing is we have an idea that let's say E of A is called estimator of A Okay. And E of A is some function of all these variables. Okay. So, E of A is some function of x1, x2 up to xn. Okay. So, suppose you have a quantity A. So, A is some quantity. Okay. Some quantity, when I say some quantity, it might mean it might be average, it might be standard deviation, etc. Okay. And E of A is some function of E of A is called the estimator of A. The estimator of A is some function of these variables, of these measured quantities. Okay. So, let's go ahead and do some estimates. First estimate we will be doing is the mean. So, mean. Okay, so the first estimator we will be doing is to give the estimator of x0. So we want to estimate the value of x0 from these measurements, from all these measurements. Okay, and the estimator of the if you follow the procedure using the maximum likelihood method, which I have not done. Okay, but using a formal procedure, you can show that the best estimator for x0 okay, is E of x0 is equal to x1 plus x2 xn by n. Okay. So, the most likely value of x0 is just the mean of these measurements. Okay. So and this is something that is very obvious, that suppose I give you a bunch of measurements, then if I ask you what is the most likely value of this variable, you will always say it is the mean of those measurements. Okay. And so this is the most likely estimator of these most likely estimator of the mean. Okay. So note, I want you to note a couple of things. First one is that we are assuming that f of x is a Gaussian. Okay, f of x is a Gaussian. Okay, in the sense we are assuming that in other words, normal distribution. This is called a normal distribution. Okay, so we are assuming that the variables are distributed according to a normal distribution. Okay. Second, and this is a more important thing to keep in mind whenever you are making measurements, is that we are assuming that the measurements of x1, x2 up to xn are, and I will use two words here. First is independent, and I will use another word, uncorrelated. Okay. So, they basically mean the same thing, and both these are very commonly used terminology. Okay. So, you are assuming that all these measurements are completely independent. Okay. That means the first time you measure x, that does not affect what you get the next time. Okay. And the next time you measure it does not affect what you get the third time. Okay. So, each of these measurements are completely independent of each other. Okay. Now, I want to say that you have to be very careful to ensure that all these measurements are independent. You have to do your experiment very carefully. Okay. So, this property of these variables is a direct test of how well your experiment is done. Okay. And if you do it the right way, then you will truly get independent or uncorrelated measurements. Sometimes you might be forced to do your experiment in ways where you do not get exactly independent or uncorrelated measurements. Okay. And then in that case you cannot use this estimator for average. Okay. Just to give an example of a measurement where in which your various values are not independent. Just imagine that you are doing a titration. Okay. And let's assume that you have you have this beaker, and in this beaker you measure the volume. Okay. So, the first time you measure a volume, okay, then you throw this beaker away and you again use it. Okay. So, if you throw the sample in the beaker and then you use the beaker again, then the next time you measure it, you are likely to have some small amount of that substance. Okay, some small amount of that substance. So, then your titrated volume will turn out to be less. Okay. So, if the flask in which you are carrying out the acid base titration, okay, if that is being reused every time, then there is likely to be some amount of the acid or base left in that, and that is going to give systematic errors. Okay. So, then your measurements are not completely independent of each other. Okay. There are many such examples you can think of where your measurements might not be completely independent of each other, but in such cases you don't use this averaging procedure. So you try as far as possible to make sure that your measurements are completely independent of each other, and then you can use such an averaging procedure. Okay. Next we want the best estimate for sigma, okay, is estimator of sigma is equal to sum over I equal to 1 to n xi. I'll call this x bar, xi minus x bar square. Okay, and I'll divide this by n minus 1. Okay, so this is something that you have seen before. So the best estimator for sigma is xi minus x bar square divided by n minus 1. Okay, and you should pay attention to the fact that it is n minus 1 and not n. Okay, now I'll just try to give you an idea why it should be n minus 1 and not n. So why sigma or sigma square? This is the best estimator for sigma square, the variance. Okay, why sigma square? Sigma square has 1 over n minus 1, not 1 over n. Okay, because it looks like each of these is a square deviation. So, the average square deviation should seem like 1 over n times this, but in fact the best estimator for sigma, so for sigma square, is not the average square deviation, but it's the sum of square deviations divided by n minus 1. Okay. So, now actually you can show that this is the best estimator of sigma using the maximum likelihood method, okay, which I have not discussed, but there is a formal way to derive this. Okay. Now, I am not going to do the derivation, but I want to point out one important thing here, okay, which will help you understand why you should have n minus 1. That is the following. Now, in this estimator for sigma square, you have an x bar, okay, and x bar is actually an estimator. X bar itself is an estimator. Okay. So, this is an estimator for x 0. Okay. So, x bar is an estimator for x 0. Okay. So now if instead we had used sum over I equal to 1 to n x minus x 0 square. Okay. So, if we had used sum over I equal to 1 to n x minus x 0 square, this is the true, this I will call the true mean. Okay. So, if there was some way you knew the actual value of the mean, if there was some way you actually knew what the mean was, not and the true mean will in general not be equal to x bar. So, if you actually knew the real mean, okay, then you would use 1 over n. Okay. But since you estimated the mean based on these measurements, okay, since you already estimated the mean based on these measurements, then it turns out that all these n values of these deviation are not completely independent. Okay, there are only n minus 1 of them that are independent. Okay, because all these because the sum of all these deviations should be 0. Okay, because that is the definition of xi bar. Okay. So therefore whenever you use an estimator for x 0, okay, whenever you estimate the average, you should use 1 over n minus 1. If you know the true mean by some other method, okay, if there is some method that helps you actually calculate the true mean, okay, without using these measurements, okay, then you use 1 over n. Okay. So, for example, if you say that you know that the height of some person is 6 feet 1 inch, okay, and let us say you know that that is exactly 6 feet 1 inch. Now you make a measurement, okay, you make 5 or 6 measurements, and each time you measure you'll never get 6 feet 1, you might or you'll get something spread around 6 feet 1, and you take an average of those measurements, then it won't be exactly equal to 6 feet 1. It might be slightly different depending on the quality of your measurement. Okay. But you know that the true mean is 6 feet 1. Okay. So then you can do your standard deviation using this estimate or using this estimate. Okay. So if you know the true mean, you use this estimate. If you do not know the true mean, then you use this estimate with an n minus 1. Okay. And this is a very important idea, and so I will just say why not 1 by n. This is because we are using estimate for mean. Okay. So since you are using an estimate for this mean, okay, then this should have 1 over n minus 1. Okay. So now that we have the two most important estimates, and these are the most common estimates. So E of x0 and E of sigma square are the most common estimates. Most commonly used estimators. Okay, so most cases you assume that your data satisfies a normal distribution, okay, and you assume that your each of your measurements is completely independent of each other, and you follow this procedure and get estimates for the mean and estimates for sigma square. Okay, so how do you use this? The way you use this is very simple. If somebody asks you what is your measured value, then you say the best guess for the measured value is this average. Okay, then if somebody asks you what is the variance, then you say the best estimate for the variance is this. Okay, so that's how these quantities are used. Okay, now I mentioned something about independent and uncorrelated. Okay, it is again it is really a test of how well the experiment is done to make sure that your measurements are independent and uncorrelated. Okay, and there are other cases when you actually have correlated data that you want to measure. You want to measure the actual correlations, but those are not things that I'll be covering. Okay, so next what we want to do is to estimate the errors in these measurements. Okay, so next estimate errors. Okay, so in these two, in this x bar and sigma, we estimated the parameters of the distribution function. Okay, now we want to estimate what are the possible errors in these estimates. Okay, so estimate errors in these estimates itself. Okay, and this is the next topic, that is error estimation. Okay, so I'll just give the result for the estimation of the error in this measurement. So the statement is, so best estimate for x0 is E of x0 is equal to x1 plus x2 xn by n. Okay. And the estimated error in this x bar. Okay, so then suppose somebody asks you the question, what's your estimate of how erroneous x bar can be? Okay, how erroneous x bar can be, and this is given by sigma divided by square root of n. Okay, it's given by sigma divided by square root of n, where sigma square, I'll call this sigma bar square. Yes, and this is sigma bar by n. Okay, this is equal to sum over I equal to 1 to n xi minus x bar square, okay, divided by n minus 1, the whole thing. Okay, so the estimate for the error estimate in x bar. Okay, so this is the error estimate in the reported mean value. Okay, so this will be typically the reported value of x0. Okay. So this is the error estimate in x bar, in the reported value of x 0. This is sigma bar divided by square root of n. Now again this is a very tricky issue that you notice is that why do you have the square root of n in the denominator? Okay, so why isn't just sigma a measure of the estimate in x bar, of the error in x bar? Okay. The answer is the reason why it is not just sigma is that this is the estimated error in the reported value of the average. Okay. Now suppose I make a single measurement, suppose I made only one measurement, okay, and then the error estimate for that one measurement will be related to sigma. So error estimate for any one of these measurements is related to sigma. Okay. But the error estimate for the average is much smaller than the error estimate for a single measurement. Okay, so what I mean is suppose you had these n measurements and somebody asks you estimate x 0, and you just choose an estimate which is just one of those measures. If you just say x 1 is an estimate for x 0, okay, that is also an estimate for x 0. Okay, but it is not a very good estimate, because the error in x 1, the estimated error in that will be of order sigma, which is much greater than this estimated error in this. Okay, so this idea of how to get your data and calculate the best estimates for average and calculate what is the error estimate in that is a very important role. In fact any measurement you take, you should always be careful to do this analysis. Okay. So now next what I want to show is how you take this analysis, how you take various measurements and how you report them. Let's say if you want to report them in a lab report or in a scientific journal or in a book. Okay, then what should you report? Okay, so if you have a bunch of measurements, and then how should you report those the result of those measurements? Okay, so suppose you have a bunch of measurements. X 1, x 2 up to x n, okay, and you want to report your data. Okay, then what you say is that you'll say that x 0, okay, so the best estimate for x 0, okay, is x bar, okay, and then what you want to say is so this is the best estimate for x 0, and the best estimate for the error in x bar is equal to error estimate. Okay, so that is sigma bar by square root of n. Okay, so then what you do is you say that your reported value is equal to x bar. So you say that my value is x bar, and then you say plus minus sigma bar by square root of n. Okay, so that's how you report the errors. Okay, now what this means is that the implicit in this is the assumption that your f of x is distributed as a Gaussian with mean x bar, okay, and this and with mean x 0 and standard deviation and the standard deviation. Okay, so this is of order sigma. Okay, so now what this means is that when you look in this range from plus minus sigma bar by square root of n, okay, then you can say that a large number of the values will be within this range. Okay. So if you make, so making more measurements improves error estimate. Okay, so in other sense, it decreases the error estimate. That is, it improves the estimate. Okay, estimate of mean. Okay, so as you go, as you make more and more, what we are saying here is that if you what you are reporting values of fx bar. Okay, you are reporting values of x bar. Okay, and this is your estimate. Estimate is based on the average. Now let's say you make 10 measurements, you end up here. You make 11 measurements, you might end up somewhere else. You make 12 measurements, you might end up somewhere else. Okay, and this width will be this width of order sigma bar by square root of n. Okay, so as you make more measurements, your x bar will also change. Okay, and your width will become narrower. Okay, and this plus minus, so you can only be sure of x bar up to this interval. Okay, so you might have seen some reported experiments. So reported experiments you might have seen, for example, the charge on electron, okay, is equal to so 1.602 plus minus 0.001 into 10 power minus 19 coulomb. Okay, so you might have seen things like this. Okay, so you give the estimate and you see how much the error is. Okay, now this error estimate decides significant figures. In reported value. Okay, so the error estimate is what decides how many significant figures you will use in the reported values. Okay, so if you are, for example, if we had error estimate is equal to 0.01, okay, then value cannot be written in more than 2 digits after decimal. Okay, so you cannot have something like 5.345. So you cannot have x bar equal to this, not possible. So this is not possible. Okay, because your error estimate is plus minus 0.01. So if you say x bar equal to 5.345 plus minus 0.01, okay, then what it means is you don't know whether it is 5.33 or 5.35. Okay, then it doesn't matter what you say. So this 5 is completely immaterial. Okay, so the correct way to report is report x bar is equal to 5.34 plus minus 0.01. Yeah, 5.34 or 5.35 plus minus 0.01. Okay. So you can never be sure whether it is 5.35 or 5.5, it can be anywhere between 5.33 and 5.35. Okay. So most of the times you measure it, you will get between 5.35 and 5.33. Okay. So this is something that you should keep in mind whenever you write your laboratory reports. You pay special attention to using the correct number of significant figures in those measurements, and also always try to estimate what your error is. Even if you have made a measurement only 3 times, you go ahead and you calculate the error estimate. Okay. So calculate this sigma bar by square root of n using the formula we have discussed. Okay. So now the last thing I want to talk about is what are the sources of error in your measurements, and in particular I'll discuss 2 kinds of errors, and it's again extremely important that you keep a track of these in any measurement you make. Okay. So the two commonly encountered errors in any measurement are what are called the systematic errors, and the second kind is what are called the statistical errors. Okay. So the systematic errors are truly errors, they are not completely independent, they are errors because you are making some genuine mistake, okay, which you cannot help making. Okay. So for example, if you are measuring the density of water, okay, now you cannot control let's say your apparatus does not allow you to control the temperature outside. Okay. So you are measuring the density of water, and you cannot control the temperature outside. So when the temperature outside changes, your measurement will give you you will get a different measurement. Okay. So then you are generating errors in your experiment because of changes in temperature, and the temperature outside let's say it changes in some systematic fashion. So then you will get some systematic errors. Okay. So these are typically cannot be analyzed using statistical methods discussed so far. Okay. So these errors are not you cannot, so whatever systematic errors you get, you cannot analyze them using these statistical methods like mean and variance and so on. Okay. So these are these have to be minimized. These have to be either minimized or corrected. Okay. So whenever you know that you are going to get some of these errors, then you correct your results for these errors. Okay. So for example, if you let's take the example, you are measuring the density of water in a lake. Okay. Now that will change as the temperature outside changes, it might change. Okay. So you correct for the fact that the temperature outside is changing, and you correct it in the estimate. Okay. And then you can use various ways to correct it. Okay. But this is completely different from this statistical errors. Okay. So the statistical errors, these are random. Okay. They are completely independent of one measurement is completely independent of another. So completely independent measurements Okay, this can be estimated using statistical tools discuss. Okay. So, so you can estimate the statistical errors, okay, using these tools that we have discussed, like the mean and the variance. Okay, but all your systematic errors are ones that you have to correct for. Okay, and it's very important to distinguish between these kinds of errors. Okay, and so whenever you make any measurements, you want to either minimize the systematic errors or you want to correct for them. Okay. Similarly, when you do statistical errors, you want to estimate them. Okay, and if you make more measurements, then the statistical errors will keep going down. Okay, so these keep decreasing as more measurements are made. Okay, and this is typically true. Okay, it's not always true. Okay, typically they keep decreasing as you make more measurements. Okay, whereas these they typically do not depend on whether you make some or more measurements. Okay, so we'll keep this in mind, that we always try to minimize the systematic errors. Okay, and or you correct for them. Okay, and whereas the statistical errors are those that are estimated, and they can be reduced by making more and more measurements. Okay, so whenever you do any experiment, you always identify what are the sources of error in your experiment. Okay, so it's a standard exercise to go ahead and identify what are the various sources of error, classify those errors into systematic and statistical errors. Okay, and then you make this correction. Okay, and the final thing I want to mention is what is the phrase that is used is data. Okay, data implies statistical errors. Okay, so suppose somebody says I have data on this measurement, then the normal implication of data is statistical errors. Okay, not systematic errors. Systematic errors are usually corrected data. Okay, so statistical errors and all systematic errors are corrected. Okay, so once you have corrected your measurements of all systematic errors, what you have left is only statistical errors, and then you can call them data. Okay, and then they only have statistical errors. Okay, and though we used most commonly used is the normal distribution. Okay, so we fitted our data, we estimated parameters for the normal distribution. You can also estimate parameters for other sorts of other distributions. Okay, and I won't be doing that. Okay, but all this can be done using the maximum likelihood method. Okay, so to summarize, what we have, I want to mention that the maximum likelihood method is a way to estimate the errors. Okay, even if and what we have seen is we have not actually gone into the details of the maximum likelihood method, but we have taken the results and seen how to use them in any practical applications. Okay, so whenever you look at any reported values, you will always see the value of A is equal to some number A0 plus minus A1, and this is our average, and this is the error estimate. Okay, and more another very common thing that you will observe is that in graphs error estimates are shown as as error bars. Okay, so for example, you might have a graph of values. Okay, and what is done is typically, suppose you measure your rate constant as a function or your rate constant as a function of temperature. Okay, then you'll get various numbers, and so you'll get a graph with various numbers. Okay, now each of these numbers corresponds to one data. So this is a result of many measurements. Okay, so each of these numbers is a result of many measurements, and so this is the mean value of all those measurements at this temperature, and then there is usually an error estimate. So the error estimate is shown like this. So that means this measurement is the mean value, and so it is plus minus this, so plus this to minus this. Okay, so then these error estimates are often shown in measurements. Okay, and these error estimates are very important at times. Okay, so when you want to say whether the difference between two values is significant. Okay, so notice that the error bars, when the error bars overlap, okay, then you say that there is no difference between these two values. These two values are almost the same. Okay, so whenever the error bars overlap, so this goes all the way down to here, and this goes up to here. So then in this region their errors overlap. Okay, and when you see that their error estimates overlap, then what we said is that you cannot tell whether this is here or here. You cannot tell where it is. So then you cannot tell that this is different from this. You cannot tell that these two measurements are different. Okay, so this is another important part of analyzing various experimental data. Okay, so if you get two graphs, if you plot your results and you get one graph like this and another graph like this, okay, then the first thing you should do is you should look at the error estimates. Okay, if the error estimates are smaller than if the error estimates don't overlap, okay, then these two are different. Okay, so the error estimates do not overlap, then these two values are different. If the error estimates overlap, then you say that you cannot tell that those two values are different. Okay, so then you can do two things. If the error estimates overlaps, you make more measurements. So when you make more measurements, the error estimates will go down. Okay, so when you make more measurements, the mean value might go up or down, but the error estimate usually goes down. Okay, and then you can tell when these values are significantly different. Okay.